welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am an associate professor from Department of Computer Science, Aryabhat College, University of Delhi. So, our current topic is Huffman Codes. This is actually a classical application of the greedy technique. So, have you ever wondered that how this zipping of files is going to compress the size? So, that is being done with the help of compression techniques, and Huffman is one of that. Huffman coding is one of that compression techniques. Huffman coding is a technique of compressing data to reduce its size without losing any of the details, and it was first developed by David Huffman. That is why the name Huffman coding. Huffman coding is generally useful to compress the data in which there are frequently occurring characters. So, for this is a good coding scheme for compression of the text data, because in text data there are so many letters, there are so many characters which are very frequently occurring. So, in English language, if you can say R, E, A, these are the characters which are used very frequently. So, let us see with the help of an example that how this Huffman coding works, and then we will look into that how greedy techniques comes into the picture. So, for example, let us see that the string which is given on the screen is to be sent over a network. So, here we have B, C, A, A, D, 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 C, C, A, C, AC and AC. So, here we have taken this as the initial string, and here the 4 characters which are A, B, C and D are having different frequencies, and each character, if we see in terms of memory, is going to occupy 8 bits, and total, if you can see in this initial string, there are 15 characters. So, 15 multiplied by 8, this whole string is going to require 128 bits if we want to send this string over a network. So, what is the can we reduce this size of this string without losing any of the information? So, yes, this can be done using Huffman coding technique. We can compress the string to a very smaller size than what is what the size is, what is the present size, which is 120 bits. So, Huffman coding first creates a tree using the frequencies of the character and then generates the code for each character. That means we need to calculate, or we need to find out the frequencies of these characters, and then frequencies of these characters will be stored or will be used in order to generate kind of a tree of those characters or those frequencies, we can say, and then a character or the kind of code for each character is to be calculated. So, once the code, the data is encoded, it has to be decoded, and decoding can also be done using the same tree. So, Huffman code prevents any ambiguity of decoding process using the concept prefix code. Prefix code says it is a code associated with a character which should not be present in the prefix of any other code. So, Huffman code prevents any ambiguity, and that is why I have told you that this is a technique in which you are not going to lose any information, and the tree which is being created with the help of frequencies is going to help in maintaining this prefix code property. So, Huffman code is actually a prefix code in which a code associated with a character is not present in the prefix of any other code. So, that means there is no we can say there are no chances of any such confusion. So, if we look into that initial string of 15 characters which is shown on the screen, and if we are going to calculate the frequency of these characters. So, here we have 4 characters A, B, C and D, And if we look into the frequency, so here is the frequency of all the characters in the screen. So B is used only 1 times, the frequency of C is 6, A is having the frequency 5, and D is used 3 times. So C is having the highest frequency, followed by A, then D, and then B, if I am talking about that particular that initial string which I have shown you. Now what do we need to do? We need to sort the characters in increasing order of the frequency. So increasing order of the frequency, if I say, so 1, 3, 5 and 6, which are the frequencies of B, D, A and C. So characters are sorted according to the frequencies. Then these characters, or we can say these frequencies, are stored in a priority queue. So first of all, the frequency is to be calculated, then a sorting is to be done as per the frequency, and then a priority queue is in the picture in order to store these. Now we are going to make each unique character as a leaf node and create an empty node Z. Assign the minimum frequency of the left child of Z and assign the second minimum frequency to the right child of the Z. Set the value of Z as the sum of the above two minimum frequencies. So how are we going to do this? So here let us say we have these characters. So we have 5 and 6 which are the frequencies, then and we also have 1 and 3 as the frequency of B and D, 5 and 6 as the frequency of A and C. So we will start with minimum frequency, which is 1 and 3. Now we have created an empty node, let us say Z. Here I have denoted that with the help of a star. So the left side of that empty node, or the left child of that empty node, is B, the one with the minimum frequency. The right child of that empty node is 3, or D we can say, or the character D with the second minimum frequency, and the value of the node Z will be the sum of these frequencies, which is nothing but 1 plus 3. So we have taken 2 minimum frequencies. The best minimum frequency is on the left side of the or as presented as the left child of the node. The second minimum frequency is presented as the right child of the node, and the value of the node is the sum of these two frequencies. And after getting sum of these two frequencies, that node is actually added onto that priority queue. So the priority queue earlier was having we can say 4 elements, which are 1, 3, 5 and 6, and these are nothing but frequencies of B, D, A and C. Now that frequency, now that priority queue is holding 3 elements, which is 4, 5 and 6. So 4 is nothing but the sum of 1 and 3, which are the two kind of minimum frequencies. Now here that you can see on the screen. Moving further, if we kind of take it further, we are going to repeat this process for other nodes as well. How? Let us see. So here we have removed the 2 minimum frequencies from that priority queue and add the sum into list of frequencies. We have also inserted the node Z into the tree, and then we are going to repeat the steps, these steps for all the characters. So in order to repeat the steps for all the characters, here on the screen, if you can see on the left side, I am having a node whose value is 4. Now I have picked the minimum frequency available in the priority queue, which is nothing but 5, and that is the frequency of A. Now I am having 2 nodes, one with frequency 4, which is actually a sum of we can say the two minimum frequencies, and another one is the node with the value 5. So, the addition of this 4 and 5 will be 9, 4 will be the left child and 5 will be the right child, because 4 is lesser than 5, and the minimum value we are going to keep on the left side, and the bigger value we are going to keep on the right side. So, 4, which is the addition of 1 and 3, will be on the left side. The second minimum frequency 5 is on the right side, and the addition is 9. Now, this addition is being kind of again added into or again inserted into the priority queue on its proper position. If you can see on the screen, earlier the value was 4, and hence it was kind of inserted on the left side, or we can say at the front of the queue. Now, here the value is 9, so that 9 is to be kind of inserted in the inserted at the end, and this being the priority queue, we can have elements as the and these 6, 9, 4, 5, 1 and 3, these are nothing but the priority values. So, now we are left with two elements. One is the kind of this particular node which we have denoted with star, it is having the value 9, and another one which is kind of C having value 6. So, now when we are going to kind of add these two nodes C and this temporary node which is denoted by star. So, C is having value 6 and this star is having value 9. So, C will be on the left side of the resultant tree and this 9 will be on the right side of the resultant tree. So, here if you can see on this screen, so we have 15, which is the sum of 6 and 9. 6 is the frequency of C and 9 is the kind of resultant tree which came as 1 and 3 gives 4 as the node, then 4 and 5 gives 9 as the node. Now, finally 6 and 9 are going to give 15 as the node. So, here we can say is the complete tree. Now, how we have kind of computed or how we have drawn this tree is, let us try to revise. We have calculated the frequency of all the characters in the string which is to be sent, or in the text which is to be sent over a network, or maybe which is to be compressed. Then all these frequencies are actually sorted, and then they are put up into a priority queue, and by taking the two minimum elements from that priority queue, we are going to sum up. So, initially we have taken B and D, the sum is 4, along with this 4 we have taken 5, the sum is 9, and along with that 9 we have taken 6 and the final sum is 15. Now, here is a tree which is kind of, we can say, ready. Now, what do we need to do? We need to provide a code to this tree, so that all the characters can have some specific non-repetitive prefix code. So, for each non-leaf node we are going to assign 0 to the left edge and 1 to the right edge. So, starting from beginning, if you can see, we are going to assign 0 to the edge which is connected to the node with the frequency 6 and it belongs to C. Then we are going to assign 1 on the right side which is having 9. Then similar procedure on the lower levels of the tree. So, each non-leaf node we are going to repeat the same process. So, on the left side of 9 we have given the edge as 0, on the right side of the 9 we have given as 1. Then coming to the node with the value 4, the left side is 0 and the right side is 1. So, in this way we have kind of we have assigned the characters or assigned the numbers 0 and 1, 0 to the left edge, 1 to the right edge for this whole particular tree, and this is what we are going to do for each non-leaf node. So, how are we going to generate the character code from here. So, character code for C, if you can see in this on this screen from this tree, is going to be 0. Then for A, it is going to be 1 1, which is actually the path starting from root to that particular node. If we talk about B, it is going to be 1 0 0. So, 1 between 15 and 9, then 0 between 9 and 4, then 4 between 4 and 1, it is 0. So, we will start tracing the path from root to that particular node. Whatever 0 and 1 we are going to encounter, that is going to be that is going to be the character code for that particular character in the initial string. So, for C we have 0, for B we have 1 0 0, for A we have 1 1, and for D we have 1 0 and 1. So, this is going to be the code which is kind of a compressed code. So, for sending the above string over a network, we have to send the tree as well as the above compressed code, and the total size, if we talk about, here you can see we have A, the frequency is 5 and the code is 1 1, 2 bits. So, 5 multiplied by 2 gives us 10. If we talk about B, the frequency is 1 and the code is 100, which is 3 bits. So, 1 into 3 is 3. Then C is 6, the frequency for C is 6, the code is 0. So, 6 multiplied by 1 bit, which is equals to 6, and then D, for which the frequency is 3 and we have the code as 101. So, 3 multiplied by 3 bits is 9. So, the total size here is coming out as 28 bits, and then this 4 into 8, 32 bits for the characters, and then 28 bits we have we can say we have compressed, we have given the code. Now, what is the speciality about this particular code? The size of the code is actually we can say is inversely proportional to frequency. Higher the frequency, lower is the size of the code. So, if we have frequency as 5, the code is 1 1, the frequency as 1, the code is of 3 bits, frequency of 3, code is again is of 3 bits, frequency of 6, the code is 1 bit only, and this being the prefix code is leaves no chances for anomaly. So, here if we talk about how much are we going to get, at least as far as this example is concerned. So, without encoding, the total size of the string was 120 bits, and after the encoding the size was reduced to 32 plus 15 plus 28, which is equals to 75, because we need, along with this tree, we need to send these codes also. So, the total size has been reduced from 120 to 75, and for just a 15 character initial string, this we can say is just actually kind of an improvement. But this was first part, or this was kind of half part of the whole procedure, because we also need to see that how are we going to decode the characters. So, in case of encoding the characters, what we did till this point is we have taken in string, calculated the frequency of each particular character, sorted those frequencies, we have put up those frequencies in the in the priority queue, take 2 minimum frequencies, keep them at the leaf nodes, add them, and then keep on building your tree in a bottom up manner. After building the tree, we need to assign the character codes. So, in order to assign the character codes, we start from root node, going in the bottom direction or going in the direction down towards the leaf, we will encode 0 to the left edge, 1 to the right edge, and then so on and so forth. And finally, we got the character codes for all the we can say all the characters which are available as the leaf nodes of that particular tree. Now that string or kind of that coding along with the tree has been kind of we can say sent over, but at the receiving end we need to decode that code also. So for decoding the code we need to traverse through that particular tree in order to find that character. So how are we going to do it? Let us say 101 is to be decoded. So in this tree, if you see 101 is the kind of code for D. So if you need to decode 101, we can traverse from the root as we have shown in this figure. So 101. So initially we will start from we can say the right side. So we will look for the first edge on the bottom side, which is representing 1. That is the edge between 4 and 3, if you can say, that is 1. Going in the up direction, we look for the edge which is representing 0, then we have between 4 and 9, or even we can, if we start from kind of 15, we have 1 0 1. So we can traverse it from the root, or we can say the idea here is the better idea here is to start from the root. So 101 we start from 15. So 15 and 9 is the edge is 1, then between 9 and 4 the edge is 0, and between 4 and 3 the edge is 1. So we will start from the root, not from the bottom. So 1 0 1, and we will end up with the character D. So 101 is the code for D. In order to kind of trace it for, let us say the code 11, we will start from the root again. So between 15 and 9 we have 1, then between 9 and 5 we have 1 again. So here is kind of the character which is represented by 1 1, which is nothing but A. Now in the inception I have told you that this Huffman code is actually an application of greedy technique. Where is that greedy technique? So greedy technique, if you can see that we have sorted the frequencies, put them up into a priority queue, and we have taken the 2 minimum frequencies in order to construct the this tree which is representing this character code. That's where your greedy techniques pitch in. You are taking 2 minimum frequencies, and the greedy choice here is to take 2 minimum frequencies, and those 2 minimum frequencies are being added. Now that frequency is kind of added to the queue. Again 2 minimum frequencies are being taken out, and just because of this pulling up for the 2 minimum frequencies, we have used priority queue, because priority queue is the kind of we can say the most appropriate data structure for this kind of operation. So Huffman coding actually a classical example of greedy technique, and which is actually a compression technique. We can say it is a lossless compression technique, in the sense you are not going to lose any information when you start decoding, or at the receiving end, if we say. So in this lecture we have looked into the Huffman coding as a classical example of greedy technique. We have looked into what is this Huffman coding is. Then we have taken an example and tried to we have coded all the characters in that particular string. We have also decoded all the, we have also seen the mechanism to decode that string, and we have seen, apart from that, we have also seen that how much is the benefit which we are going to get in terms of compression. So, Huffman codes initial string was the example which I have taken in my lecture. 120 bits was the initial uncompressed size. After getting compressed it through Huffman code, the size reduced to something 75 plus something. So, that is actually we can say a benefit if we talk about only that much of an string which is having 15 characters. Now, you can see this magnitude, or you can imagine this magnitude in terms of large text. So, yes, Huffman coding is actually a very important concept when you start learning about various coding schemes, and that is what we have learnt in this particular lecture. Here is a list of references which is being used for the preparation of this talk. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.